Okay, guys, I decided to go ahead and do this by hand rather than put on the dossier. I have a dossier made for you, but this is the only way that I can actually make a video without having you guys need to go to YouTube. I know you are technologically savvy and are capable of doing that. I just don't want to have to bother with the extra cables and stuff. So, here we go. This is our first true vector lecture, so we're going to talk about vectors and get zoomed in better. Vectors, and in particular, we're going to start with our coordinate systems. There we go. Coordinate systems. Then we will move on to vectors and scalars. And then the properties of vectors. All right. So, real quick review. We have been working in one dimension, and so let's draw our number line here, our x-axis. So this is x in meters, and we have -1. Okay, they're all pretty much the same space. And so we start, let's go -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. And then we start, let's say we start at 3 meters. We have a particle that starts its motion at 3 meters. Well, we initially start, we identify this place, we communicate this spot as a position vector. And it is a distance from the origin. And so his initial position then, okay, is, x initial is going to equal 3 meters, a positive 3 meters. And then he decides to move all the way down here, and this is this gives him a final position of -2 meters, and that negative implies that the vector is going the other direction, okay, to there. And so we have a final position of -2 meters. And so both of these are position vectors. They're just where something is. It's sort of talking like 0D. It's just where something is in respect to the origin. Okay, but we know that our delta x, our displacement, is the difference between the two. So our delta x equals x final minus x initial. Okay, which in this case is our -2 meters minus 3 meters, and this is, that's a -5 meters, and this is his displacement. This is when he goes from one position to the other. Okay, that's how we get, we have this -5 meters, but the -5 meters is his change, and this is related as that vector right there. We start at the 3, we move to the -2. That is a -5 meter displacement vector. Okay, and that vector right there, this is x initial, this is x final, and this is delta x, and it's that vector. Okay. However, things don't exist in one dimension. We would have a very boring place if the universe was in one dimension. We couldn't really go anywhere. We'd just be standing in line behind everyone else, and everyone else would be standing in line with us, and that is only if we had a circular universe. Okay. Otherwise, it would just be a straight line, long line road to nowhere. So, instead of that, we have, our coordinate systems for position. Okay. We have a coordinate system for position, and that is, well, I have my ruler sitting out, so I'm actually going to attempt to do things somewhat orthogonally, or at least create straight lines for you guys. So if I'm expecting you guys to use graph paper, maybe it's only fair that I hold myself to that kind of a standard. So, all right, and here's our x-axis and our y-axis, and we have this spot right here. How do we communicate where this is with respect to its position? How do we do that? Well, one way to do it is how far away is it? Okay, and so we start at the origin and we create our vector like so. Okay, and that how far away is the magnitude of the vector. Okay, so the magnitude, okay, is how far away. That equals our magnitude of the vector. And then in which direction? Which direction is it? Well, that's our direction, and we can say that it is going to be, okay, well, we have to agree to a place from which we're going to measure our angle. And by convention, we use the positive x-axis as our basis for measuring our angle. So in this case, it's going to be, and I could actually measure that if I wanted to. I'm not sure I can get in here and, here's my protractor, so if I'm going to put that on 180, and it looks like it's going to be, what? It's going to be 32 degrees, looks like. So 30, I'll call it 30 degrees just for argument's sake and because it's a nice trig number. So, okay, and we call this theta. Okay, and so imagine this would be the angle, okay, or our reference angle. Okay, and we call this vector, the position vector of something, we're going to call that r. And it does stand for radius, okay, because you can have that distance, okay, we'll call that distance r, and everything with the distance r is going to be in a circle around the origin, so that's why we call that vector r. And what we have here is a polar coordinate. So if we have the magnitude and the angle, we have r in terms of our magnitude and our direction, and this is in polar coordinate. Oh, and I'm off the screen. So this is in polar, this is a polar coordinate, or this is in polar coordinates. Okay, now there's another way of doing this, and it's time to bust out the ink here. So the other way of doing this is we can measure, or we can break this up into what's called components. Okay, and it has one component along the x. Okay, and we will call this, it is the r, that is the component of vector r in the x direction, and then we have that, which is the component of r in the y direction. Okay, and that is, and so we have these two components, and in this case, our rectangular coordinate, we can have a rectangular coordinate okay, a rectangular coordinate r is our x ry Okay, so we have a component in the r direction, and a component in the x direction, and a component in the y direction. Oh, sorry, didn't show that. So we have that right there. All right. So with those in mind, okay, how do we relate these to each other? Okay, how can we relate our polar coordinates to our rectangular coordinate? Okay, well, we do know that the x and y axes are orthogonal. They are orthogonal. Okay, and orthogonal is a fancy physics term for vector. It's a fancy vector term, sorry, for perpendicular. Okay, and okay, so fancy vector term for perpendicular, and okay, and it's actually how we can create that's how we get into new dimensions. And so we create a fourth dimension and a fifth dimension, are all because their axes are the axes are all mutually orthogonal. We create new orthogonal vectors as we create new dimensions, and we can have an infinite number of orthogonal vectors. It's just a math trick. Okay, but we can get into that later. So we can use, because they're orthogonal, we can use the mathematics of right triangles. We've got a right triangle here to relate our theta, our polar coordinates, to our x and our y. Okay, and we do that, and so here's how we do it. We start with rectangular coordinates going to polar. Okay, well, we know that. Is that getting out of focus here? So let's do it a little bit. Let's try that again. A little bit of focus. There we go. Much better. Okay. Well, we can determine what r is, because r is just the distance here. R, if we're looking for the magnitude of r from our polar coordinates, we can use the Pythagorean theorem. That's our hypotenuse. So our r is going to equal rx squared plus ry squared, and then the square root of all of that. And that's going to be our magnitude of our r vector in terms of is when we're switching over to polar. Okay, but we also know that according to this, our angle down here, we can relate to this theta, because we know from SOHCAHTOA okay, that our opposite and adjacent legs to this angle are going to give us, or our opposite and adjacents are going to give us what this angle is, because y over x will give us tangent equals y over r x. But then if we're looking for theta, what we really want to find, okay, is now we can use the other trig, the other trig identities. We can use ry over r. Opposite of hypotenuse would be sine, and adjacent of hypotenuse is cosine, and so on. But we don't really, we won't be using those that much when it comes to relating between rectangular and polar. We will use them significantly at certain parts of the class, but just not when we're converting between the two. Okay, what we will use, however, is this ry over rx equals tan theta. Okay, and if we solve for theta, because we want to find what this is for a polar coordinate, this winds up being that theta equals arctan of ry over rx, or inverse tangent of ry over rx, and that's what theta equals. Okay, so we have these two ways of finding we have these two ways of getting our rectangular polar coordinate from our of getting our polar coordinates from our rectangulars. Okay, but calculators are stupid. Okay, and we can't just throw a number into our tangent, because we get, here's our axes again with quadrant 1, 2, 3, and 4. And if we have this vector here in quadrant 1, that is going to give us a similar arctan as this here in quadrant 3. So let's see, we have this x and that y, and they're both in the positive, but it's also going to give us that other one where negative x and negative y will give us the same arctangent, so give us the same value, even though these two angles are very different. They're opposite to each other. So we need to be cognizant of which one we're dealing with. In fact, arctan only returns values in quadrants 1 and 4. 4 IV. Okay, it doesn't return them for any other time. Okay. So let's rewrite theta as this. It's the arctan of ry over rx, and then plus 180 degrees if we have a negative rx. Okay? So if x is a negative value, then we need to add 180 degrees, or pi in radians, if you like thinking in radians instead. That's going to be our new value for tangent. Okay, so keeping our diagram over here, we're now going to do polar to rectangular. And this one is a bit more elegant, if you ask me. I kind of like this one. Polar to rectangular. Okay, well, so we know that from this over here, that sine of theta equals ry over r, and we know that cosine of this theta is going to equal rx over r. So if we solve, if we're solving for ry and rx, we get ry equals r sine theta, and rx equals r cosine theta, still assuming that theta is this this reference angle down to the x-axis. If it were the reference angle up to the y-axis, then those would be reversed, and we would, but by convention we use the x-axis. So, okay, so that's what ry and rx equals. But I don't want you to take my word for it. Okay, we know that. So we have these rx and ry, but we're going to go back and convert these into polar just to prove what we're doing. So we know that r equals the square root of it's a really long square root from what I'm trying to write, so for neatness sake, square root equals rx squared plus ry squared. And in this particular case, it's going to equal the square root of r sine theta squared plus, and that was a short one, I don't have enough room there, plus r cosine theta squared. Okay, and you guys may see where I'm going with this, because we can factor out an r squared and leave behind sine squared theta plus cosine squared theta. And as you learn when we first have our trig identities, that this becomes 1, and so we're left behind with the square root of r squared, which is of course r, and so those two are equal to each other. Now, we also know that ry over rx is supposed to equal tan theta, but ry is r sine theta, and rx is r cosine theta, and sure enough, the r's will cancel, leaving behind sine theta over cosine theta, and that does equal tan theta, and that's the other proof for this. So, this brings us to measuring angles. So, I have to alter my paper here. I don't want to use this big blank one. All right, so now check this one out. This is why I like this device right here. Watch this. So we're going to have, hopefully we'll make this orthogonal. That looks pretty good. Now I'm going to put this right there, and I'm going to make a, is that right in the middle? That looks right in the middle. And check this bad boy out. Ta-da! Unit circle. All right. Here's our unit circle. This is our radius of our circle. Okay, in fact, I want to start using okay, so can you see that? You probably can't see that green yet, so you'll see it better. Okay, this is the radius of the circle, and if we were to take this, say, out of a piece of string and lay it along the edge of our circle, we would get about that distance right there. Okay, and maybe up to there. Okay, and then we extend this back, and this, what we have here, okay, let's shade that in a bit. Okay, what we have here, okay, this is R. Okay, this right here is 1 radian. The measure of this angle, if we take this arc length, if we lay this R and we measure it along here so that this arc length is also R, then this angle is called 1 radian. Okay, and because of that, this radius, if we lay it out, then we know from the circumference of the circle that the length of the circumference of the circle is 2 pi r. So if we go all the way around the circle, then that would be 2 pi radians equals 360 degrees, and that's how we get this this radian geometry. All right. So let's say we find this arc length S is what we'll call it, and it starts here, and our arc length S goes all the way around the circle to there, to that spot right there. Okay, our theta, okay, is this S, so this is arc length S. Okay, this arc length S is that total distance all the way from there to there. And if we divide that by the length R, okay, because that's how many, there's so many radians. Okay, we take that S and we divide it by R. So S distance of arc length divided by the number of radii, the number of radians in that angle, that is going to give us our theta. Okay, and this winds up being a very important concept when we start dealing with rotational material, rotational equations. Okay, now we're going to talk about scalars here. Okay, if we have a scalar, then it's just a quantity of something. It's just how much, it's how many. If you open up a bag of M&Ms and you find that you have 250 because, it's a big bag of M&Ms. Or kelvins, with Kelvin temperatures. So let's say we have 370 kelvins. That's just how many kelvins. It's an amount of, it's an average amount of energy in your particles. It's just an amount. Okay, and that's all you need for a scalar. All you need is just a value. However, in vectors, and they are a magnitude only. Okay, that is the mathematics of elementary school. 3 plus 4 equals 7. Okay, vectors, however, don't work that way. Vectors have a magnitude and a direction. Okay, and a direction. Corey Hunter, I know you're laughing at that. Okay, a direction. So, okay, so now we have to learn the mathematics of vector quantities. So, as scalar math, we knew that 3 plus 4 would equal 7. But, and it's always that in scalar math. In vector math, our 3 plus 4 could equal, I don't know, 5? Okay, it could. Okay, and here's how it works. Okay, if we are accounting for our changes in direction. So, let's say this is a vector that is 3 long, and that is a vector that is 4 long, and these are orthogonal. I have me drawing straight lines is just difficult to do. So this right there would be 5 because you have your 3, 4, 5 right triangle. So what makes vectors equal? What makes vectors equal anyway? Well, vectors have to have the same magnitude and the same direction. Same magnitude, same direction. So if we have a vector that is given, vector A, that is given by magnitude A and theta for A, and we have another vector, okay, and that's going to look like okay, and then we have another vector B that's going to equal B and theta B, and that has a similar look. Okay, so those were not even close to equal to each other. So if we do this again, so if we have A and B and theta A and theta B, if theta A and theta B are the same size, and A and B, if A and B are equal to each other, then we have equivalent vectors. Okay, now we're going to start adding vectors. All right, so kind of new topic here. If we're adding vectors, okay, when we add normal way, we have this 3 plus this 4. Okay, and this right here is an operator that means count them all up. Okay, well, for vectors, it doesn't mean that. This means something new. Okay. So it has a new meaning when we're dealing with vectors. Okay, and this means hook them up head to tail. Okay, so when we're adding vectors, we hook them up head to tail. So let's get a new sheet out here. And where are we? All right. So we have vector A. Okay, and vector B. All right. Well, when we add them together, okay, A plus B is going to be, so I can go and create the same vector. Okay, so same angle, same length, and then I hook it up to B. So I pick it up and put it down, and I keep the same length and same angle. Okay, and this is B. Okay, and that gives us this vector, that right there, which is vector A plus B. Okay, and because we added them up tip to tail. Okay, okay, but what about, okay, that's fine, but what about B plus A? Well, let's take the same vectors, and we're going to go B, right, pick it up and plop it down, and that's pretty much the same vector, maybe tilt it a little bit, and that's B. And then we take A. Okay, this looks so much better on my dosseri because I was able to copy and paste the vectors and move them, but Here you just have to deal with my handwriting. And there's b plus a, and lo and behold, we get a vector here that this one is very similar to that one. And if I had my good drawing tools on my iPad, then you would see that they actually are exactly the same. So a plus b, okay, which b plus a equals a plus b, which means that in vector math, this says something in particular. It means that these are commutative. Vector addition is commutative. It doesn't matter. The addition doesn't matter which order you move in. However, that is not the same. Okay. Oh, it also works with three vectors. Okay, so a plus b plus c can equal r, and okay, so a plus b plus c, and so if you add these two together first, okay, so let's say we add those together and add c, we add these two together, then add a, that's going to equal the same r, and a plus c plus b, if we add those two together, a and c together, leave out b, then that will also equal r. There's no difference there, so they are also commutative in that regard too. Okay, now you may be asking yourself, okay, that's addition, what about subtraction? Well, first, before we get there, we're going to talk about negative vectors. Okay, now negative vectors have the same magnitude as their positive, but they have opposite direction. Okay, opposite direction. So if we have vector A, then negative A is going to be the same vector pointing the other way. All right, so they're exactly the same thing. Okay, why do we do this? Why are we even worried about this? Because we have subtraction. I'm sure you know it's coming, that if we add vectors, then we also have to be able to subtract vectors. So if we have vector A, okay, and say vector B, and we want to find A minus B, well, this is, for vector math, this is going to be the equivalent of A, vector A, plus, because we like the vector addition, negative vector B. All right, so we're going to subtract B from A. It is A plus negative B. Well, negative B is going to look like negative B, and then we add them together. So here's A, and then that becomes A plus negative B, and then all of a sudden this is A minus B. Okay, what about B minus A? This is A minus B. What about B minus A? Well, you can probably tell that if this is A minus B, then if we, then this would be the opposite of it, because you can multiply by negative 1, and it's going to equal negative A minus B. Okay, or it's just B plus the negative A. Okay, either one of these are equal, but either way, you're going to have B which is that direction, and we have A, okay, which is up, but in this case we're going to be down. And what do we get? We get this vector, which is B minus A, which if you compare to this one, okay, is roughly the same, just in opposite direction. Okay, keep in mind that you have to draw pretty close to scale in order to get these to work just right. Okay, or we could have just done this one and flipped it the other way, because that's what this one is. Okay, and will kind of make sense, because if you have 5 minus 3, okay, that's going to equal the negative of 3 minus 5, right? So this is 2, and the negative 2 is going to be positive 2. That should make sense to you. Okay. Then finally, we can multiply the multiplier vectors by a scalar. And if we multiply vectors by a scalar, we get, so it's just 3 times vector A, okay, is just going to equal, well, it's the same thing as A plus A plus A, right? So that's A and A and A is really just three A. And so it's just multiply. You just change the magnitude of your vector. Okay, and then if you multiply it by a negative, then let's say that's a negative 3A, then you're going to get, if A is that direction, then you're going to get negative, 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 or the full. Okay, and you just turn the vector around. Okay, now for the assignments for tonight, you may need a protractor and a ruler. Oh, I'm sorry, I didn't get, you lost that down there. So here's the negative. Negative 3 times A is just going to be 3 negative A's, or 3 times the length of one positive A. You may need a protractor for tonight's assignments, just to keep things, just to figure out what the degree measure is, and then be able to convert it to your rectangular. And that is all I have for this, and I hope this is, I want you guys to tell me how you feel about it, because I've got a couple, before I go much further with my lectures, I want to know if you've liked it on paper better than on the dossier. So let me know when I get back on Thursday. I'll talk to you guys later. Bye-bye.